All right, I'm going to go through chapter 17 homework. First one is very simple. Make sure you get the easy ones right. There's nothing at all hard about the first one. We've been doing those for, since first test. So that is 1728, where it just says give the expression for the KSP. So you have your barium phosphate. All right, so the KSP reaction is, of course, a solid going to its ions. So you will have one positive ion, you will have one negative ion. And so you got your barium ions. So you got 3 barium plus 2s, and you've got 2 phosphates. All right, and so your KSP, which is the same as a KC, this is a solid that does not go in there. Ba plus 2 raised to its coefficient of 3, and PO4 minus 3 raised to its coefficient of 2. And so that should be a very simple problem. That's part A. Part B is iron phosphate, iron 3 phosphate, FePO4, solid. And that goes to Fe plus 3 and PO4 minus 3. And so this one, your KSP, is just your Fe plus 3 raised to the first, PO4 minus 3 raised to the first. We should probably be putting these in terms of S as well. Now, if we were doing this in terms of S, so for a little extra problem here, so you start with 0 and 0. It would go to the right. You would get 3S. You would get 2S. And so you'd substitute that in, and you'd have KSP is equal to 3S to the third, and 2S to the second. That is a 3. All right, and when you multiply that out, you would get your KSP is equal to 108 S to the 5th. All right. So here you would just have 0, 0. It would be plus S. And here your KSP is simply S squared. And part C, you have silver sulfide, Ag2S. That goes to 2Ag plus and S minus 2. So your KSP is Ag plus raised to its coefficient of 2 and S minus 2 raised to its coefficient of 1. So again, 0, 0 goes to the right. You'd have 2S. You would have S. And so you would have your KSP is equal to 2S squared times S. And you plug in your S's for your concentrations. And so your KSP in this one is 4S to the third. Then the last one in problem 17.28 is lead to iodide. All right, and so that's a solid. Lead plus 2, 2I minus. So your KSP, concentration of Pb plus 2, concentration of I minus squared. Again, you would have 0 and 0. Then you would have S, you would have 2S. And when you plug that in, you have your KSP. That's S, that's 2S, that's squared. And so this one, KSP, is equal to 4S to the third. All right, so putting it KSP in terms of S, that was just a little extra work, but very important that you know how to do that. Put your KSP in terms of S, because that's what we're going to be doing for the next bunch of problems. All right, 17.32. All right, solubility of nickel 2 carbonate, NiCO3. All right, so we're talking about solubility. That's an insoluble solid. So that goes to Ni plus 2, CO3 minus 2. All right, the solubility. They give you the solubility, except they give you the solubility in grams per liter, 0.0448. When we do this one, and of course it's 0, and then it goes to the right, and you have S and you have S, and so you see here that your KSP is equal to S squared. You need to know that anytime you're writing this, and back up to the top where it was always concentration, S is a molar solubility. And what does that mean? Well, that means that the units are in molarity. All right, so molar, that means moles per liter. So it has to be in moles per liter. So if you are given a solubility in grams per liter, you will then have to convert that to moles per liter. And so when you look up your nickel, 1 carbon, 3 oxygens, add them up off the periodic table, you get a molar mass of 118.70. And so mass divided by molar mass is going to give you moles. And so we now have moles per liter. So now we have the molar solubility. And when you push the buttons for that, you get 3.77 times 10 to the negative 4. All right. So now all we have to do is now we have the molar solubility, and so we want to find the KSP. The KSP is equal to S squared. So this is still a solubility, but it's not a molar solubility. It is not a molar solubility until you put the units in moles per liter. All right, and so your KSP, remember everything in the K has to be in molarity if you are aqueous. It has to be in atmospheres if you are a gas. All right, and so you simply square that to get your KSP. And so 3.77 times 10 to the minus 4 quantity squared. Your KSP is 1.42 times 10 to the minus 7. All right. So you have to know to convert the grams per liter to moles per liter, and then have your KSP in terms of S, and then plug your S value in and get your KSP. All right, 17.34. All right, a solution saturated in calcium hydroxide. Calcium hydroxide. So calcium hydroxide goes to calcium plus 2 OH minus. All right, and so you have a pH of 12.35. So your pH is equal to 12.35. Calculate the KSP. All right, so we have 0 and 0. Then we put the calcium hydroxide in there. And now we're going to have S amount of calcium and 2S amount of OH minus. All right, so this time they don't give us the solubility. However, they give us the pH. So you have to remember that your pH plus your pOH is equal to 14. All right, and so you see that you have a 1.65 pOH. Because 1.65 and 12.35 add up to 14. And so now you can take your pOH is equal to the negative log of your OH minus. Plug in your number, 1.65 is equal to negative log of your concentration of OH minus, then you take the negative of both sides and push your inverse log, which is your 10 to the x button, and you get a concentration of OH minus of 0.02239. All right, and so how does that help? Well, that is equal to 2S. Your concentration of your OH minus at equilibrium, which is where you find your pH and your pOH, is equal to 2S. And so now you have your molar solubility when you divide that by 2 of 0.01119. So that is your solubility in molarity. That is your molar solubility. All right, but it asks for the KSP. And so we do the same thing we did in problem number 1. Your KSP is equal to your calcium plus 2 concentration, your OH minus concentration squared. So your KSP is equal to S, and it's equal to 2S squared. Your KSP is equal to 4S to the third. So you just plug in the number for S, and that is 0.01119. Raise that to the third, multiply it by 4, and you have your KSP for calcium hydroxide. And when you do that, you get 5.6 and 0 times 10 to the minus 6. I do not, unless as long as you have 2, 3, or 4 sig figs here, you will not have any sig fig points taken off. All right, and so that's how you will calculate the KSP of a hydroxide that's insoluble. You will get the pH, convert it to pOH. That gives you your OH minus concentration, and that's equal to the 2S. Once you have your S, you plug it into your 3 or your 4S to the third. All right, that was 34, 38. What is the solubility of strontium iodide, SrIO iodate, SrIO3 sub 2? All right, so you have to do what you did in the first problem for every one of these problems, Sr plus 2 IO3 minus. All right, so what is the solubility of this in water? All right, and so they give us the KSP. So we can, the KSP is equal to your Sr plus 2 concentration and your IO3 minus concentration raised to its coefficient of 2. And so this is 0 initially, then it goes to equilibrium. You have S and you have 2S. And you can put those in, that your KSP is equal to your S and then your 2S squared. So your KSP is equal to 4S to the third. This time they gave us the KSP. The KSP is 1.14 times 10 to the minus 7. All right, to solve this, you divide both sides by 4. And then to get S and only one S, you take the third root of both sides. And when you do that, you get a molar solubility of 0.00305. So there will be a question like that as well. Here's the KSP. What is the molar solubility? You have to put your KSP in terms of S. That's why I did that for the first problem, because that is very important to be able to get your KSP is equal to 4S to the third for that reaction. All right, 1742. Solubility of silver sulfate, Ag2SO4, Ag2SO4 to Ag plus, SO4 minus 2. In water is 8 grams per liter. All right, so now again, they give us the solubility in the wrong units. They give it to us in grams per liter, which is a very common way to give a solubility, but we need it in molarity. So we can easily convert that to molarity by getting the molar mass of our silver sulfate. All right, and so when we add up 2 silvers, 1 sulfur, 4 oxygens from the periodic table, we get 311.81. All right, and so we will then divide by the molar mass, and so we take and we divide by the 311.81 grams per mole, and that is going to give you your molar solubility, which is 0.02566. And now we are in moles per liter, which is your molar solubility. All right, and so it says, what is the solubility in 0.45 molar sodium sulfate? All right, so they gave us the information of the solubility so that we had to convert it to molar solubility so that we could find the KSP. So this is going to be 0 initially, 0 initially. So in water, this is going to give us 2S, and this is going to give us S. So our KSP is Ag plus squared, SO4 minus 2 raised to the first. And so your KSP is 2S squared times S. So your KSP is 4S to the third. Now we have our S value, and we plug it in. So that's equal to 4 times our 0.02566 raised to the third. Raise that to the third, multiply it by 4, and now we have a KSP for silver sulfate, and that is 6.8 times 10 to the minus 5. All right, so this problem didn't specifically say to calculate KSP, but if you looked on your chart, you would not find a KSP for silver sulfate. They gave you enough information to find it. They gave you the solubility in water. So now you have converted that solubility into a molar solubility, and then plug that into your KSP is equal to 4S to the third. So now we can do the actual problem. What is the solubility in 0.45 molar sodium sulfate? So here we have the same reaction. All right, so we have the same reaction. We have Ag2SO4 going to 2Ag plus and SO4 minus 2. Except now you have to know that all sodiums are soluble. So if you are trying to do an Na2SO4, all right, there's only one arrow. It is completely soluble. You get 2 Na plus and you get SO4 minus 2. So your initial concentration is 0.45 molar, and it is 100%. All sodiums are soluble. We have 0 of Na2SO4. We have 0.9 molar Na plus, and we have 0.45 molar of our SO4 minus 2. So you have your minus X plus 2X and plus X. And since it is sodium, 100% soluble, all of it goes to the right. There is 0 Na2SO4. All right, and so now we have an initial concentration of the sulfate. It is not 0. It is in 0.45 molar of your sodium sulfate. And so we didn't add any silver, but we do have an initial concentration of our sulfate. All right, so this is still a 0, so you have to go to the right. And so plus 2S plus S. All right, and so these are insoluble salts. S values are small. And so anytime you have a number plus or minus an S, you are going to neglect that. And then we have our 2s at equilibrium, and we have our 0.45 at equilibrium. So then we plug it in to our KSP right here, the expression for KSP. And so your KSP is equal to 2s squared for your AG at equilibrium, 2s squared, not s. It is 0.45 plus s, but s is very small, so we neglect the plus s, and we get a 0.45. And so we already know what the KSP is. It is 6.8 times 10 to the minus 5. We solve for that. All right, so to solve this one, you have to divide both sides by 0.45. That gets rid of your 0.45. And then, of course, 2s squared, you would have to divide by 2 squared, or 4. You have to divide both sides by 4, and then you would take the square root. And when you do that, you get a solubility of 0.0061. All right, but they gave the initial solubility in grams per liter, so now it will say give the solubility in grams per liter. All right, so we know the molar mass. It is 311.81, same one we had before, but this time we multiply. So 311.81 grams per mole. We multiply it so that the moles cancel. And so your solubility in grams per liter, when you multiply that, is 1.9 gram per liter. All right, so the initial was 8. So they said that your solubility is 8 grams per liter in water. Now we solve for the solubility in a 0.45 molar sodium sulfate. And it went down. It went from 8 down to a 1.9 gram per liter. All right, and so when you add a product, and that's what we did here, we added a product. The sulfate is a product. The equilibrium shifts to the left, all right, which means less is going to come to the right. And so your S value is going to be a lower value. So you need to know Le Chatelier's principle. Add a product, it's going to shift it to the left. Or that means less is going to go to the right, which means you have a lower number for your solubility. All right. 46, 17.46. From each of the following ion concentrations in solution, predict whether precipitate will form. All right, so now anytime it says predict if you get a precipitate. So anytime the question is precipitate, yes or no, you are looking at your K and you're looking at your Q. All right, and so if your K is less than your Q, that means the Q is too big, then you're going to go to the right. All right, so the reaction would go to the right. And when we're doing a KSP versus a QSP, the right side is the solid. Right side is always the solid. And then, so therefore, yes, precipitate. So asking is if you're getting a precipitate is asking, are you forming a solid? Yes. Of course, if your KSP is greater than your QSP, the QSP is too small, then it is going to go, and I should learn my right from my left because it is pointing to the left, of course. And so, yes, this one is going to the right. And then no precipitate. On the right side of the reaction, you have your solid. So let's write the reaction. And the reaction is, for the first one, strontium carbonate, SrCO3, SrCO3, solid. Of course, that is the left side, not the right side. and that is SR plus 2 and CO3 minus 2. All right, so if you're going to the left side has the solid, and that would be a precipitate. The right side, there's no solid. These are both aqueous. All right, so you have to look up the KSP value. So the KSP value for this one is 9.3 times 10 to the minus 10. All right, so that is a constant. You look it up on the table, and then you put in your concentration. So SR plus 2 initial is 0.012. And for your CrO3, or CO3 minus 2, you have your 0.0015. All right, so you have a concentration of both of them. And so you can find the Q. Remember, the QSP and the KSP have the exact same expression. SR plus 2 concentration and CO3 minus 2 concentration. The difference is if you are in the initial state, which is where we're at now, and not the equilibrium state. So if you're having numbers initially, now you have a QSP. If you are in the equilibrium state, then you have a KSP. The setup is exactly the same. So since these are initial, we're not finding the KSP because we already have that. We looked it up. We are finding the QSP, and we're going to compare it to our KSP. So we simply put in our numbers, 0.012 times 0.0015, and we get a QSP. When we multiply those two numbers, if I can read my writing, 1.8 times 10 to the minus 5. All right, so now we got to compare that to our KSP. All right, and so we have our KSP versus our QSP. So the K is a constant, 9.3 times 10 to the minus 10, 1.8 times 10 to the minus 5. And so we see that the KSP is much less than the QSP. So the reaction is going to the left. This side is the left, and that means precipitate. All right, we do the exact same thing for part B. This time we are doing lead chloride. So this time it is PbCl2. And so we're going to Pb plus 2 plus 2Cl minus. And again, you go to a table, look up the KSP, and you will find that to be a 1.6 times 10 to the minus 5. All right, so now they gave us initial concentrations. All right, so the initial concentration of lead, 0.0048. Initial concentration of Cl minus, 0.082. All right, so now this is initial, so now we're finding the QSP. That is equal to your lead plus 2 and the Cl minus concentration raised to its coefficient of 2. So your QSP, you just plug in your numbers, 0.0048 and your 0.082 quantity squared, and you get your QSP equal to 3.2 times 10 to the minus 5. All right, and so now you need to compare your KSP to your QSP. So your KSP, we looked it up, 1.6 times 10 to the minus 5. Our KSP, we calculated 3.2 times 10 to the minus 5. All right, so this one is a much closer number, except you see that the QSP is larger. 3.2 times 10 to the minus 5 is larger than a 1.6 times 10 to the minus 5. So your KSP is less than your QSP, and so again, you're going to the left, and you're getting a precipitate. So anytime the question asks, do you get a precipitate, you are going to compare a QSP to a KSP. If it is going to the left, yes, precipitate. If you're going to the right, no, not a precipitate, more aqueous. All right, 17.50. 45 ml sample of calcium chloride. All right, so we have calcium chloride. All right, and what do we know about the halides? All halides are soluble except for silver, mercury, lead. This is 100% soluble. All right, and so we also have sodium sulfate, Na2SO4. We already did this one. All sodiums are soluble. You get 2 Na plus and SO4 minus 2. These are not equilibrium. These are soluble, 100% going to the right. All right, so now we have these ions in solution, and they're asking about a precipitate. What we know is that calcium is going to go with the sulfate. The sodium is going to go with the chloride. All sodiums are soluble. So we're not talking about sodium chloride. All sodiums are soluble. The precipitate that would happen is the calcium with the sulfate. And so the question is, does calcium sulfate precipitate? And then, of course, if you're not sure, you look up a KSP. If you have a KSP value, that means you are an insoluble salt. You will never find a KSP for calcium chloride or sodium sulfate. These are 100% ionized. You will find a KSP value for calcium sulfate. And that value is 4.9 times 10 to the minus 5. All right, so if you have a KSP value, that means that you are an insoluble salt. All right, so we have a KSP, and it says, are we going to get a precipitate? And so we now have to find a QSP. So we're going to put in our initial concentrations of calcium and our sulfate and compare it to the KSP. The problem is that we have added solution to solution. And so you got to do MV is equal to MV for your calcium chloride. So we put in a 0.015 molar. We put in 45 mils, but we added that to 55 mils. And so now you need your concentration after mixing. And that is 0.0067. And so for your calcium chloride, you have 0.0067, 0 and 0, and it goes completely to the right. So minus x plus 2x. And so that 0 is going completely to the right. So we know that our x value is 0.0067. And then multiply that by 2, 4, 3, 1, 0.0. All right, and so we have our concentrations for our calcium plus 2. So it is 0.0067 molar. We have to do the same thing for the sodium sulfate. MV is equal to MV. All right, so for this one, we have 55 mils of a 0.01 molar. Now I want to know, after we mixed it, what's the molarity? After we mix it, the 45 and the 55, we have a volume of 100. And so our molarity of our sodium sulfate after mixing is 0.0055. So we have 0.0055, 0 and 0. We know that it is going to go completely to the right. All right, and so this is 0. So now we know our x value. It is 0.0055, 0.0055. If you wanted this one, it is 0.0110. All right, so we just need the sulfate. It is the 0.0055. Now we have our initial concentrations We can calculate the Q value. So that is your 0.0067 times your 0.0055. I did skip a step. Let's go QSP. Same expression as KSP, calcium plus 2 concentration, SO4 minus 2 concentration. And so we're just multiplying those two initial concentrations. And when you do that, you get a 3.7 times 10 to the minus 5. So your QSP is 3.7 times 10 to the minus 5. Again, if you're asked for a precipitate, you're looking at your KSP versus your QSP. KSP, you looked it up on a chart, 4.9 times 10 to the minus 5. The QSP, we calculated it, is 3.7 times 10 to the minus 5. All right, and so here we see that our KSP is larger than, greater than our QSP. So the reaction is going to the right, and there is no precipitate. So anytime you are asked, is there a precipitate or not, you must calculate the QSP and compare it to the KSP. $56. All right, okay, now this is where we get into some fun here. All right, what is the Cl minus concentration? So there's a lot of stuff going on here. What is the Cl minus concentration just as your Ag2CrO4, Ag2CrO4 begins to precipitate? All right, so we have our 2 Ag plus, we have our CrO4 minus 2. All right, and what we're adding is we're adding 0.9 molar silver nitrate. So you need to know that AgNO3, all nitrates are soluble. This goes to Ag plus and NO3 minus, 100% soluble. So your 0.9000, this is going to 0. It is 100% soluble. So that means we have a 0.90 molar Ag plus and we have a 0.90 molar of NO3 minus. All right, so we're going to slowly add our Ag plus. All right, so this is slowly added. So we are slowly adding a 0.9 molar Ag plus. So initially we have 0 of it. We add quarter of a drop, microliter, whatever. We're adding it very, very slowly to a solution that is a 0.015 molar Cl minus and 0.015 molar CrO4 minus 2. All right, so we have two reactions going on. We have the silver chromate reaction, and we know our chromate concentration that we're starting with is 0.015 molar. We also know that sodium will react with chloride, silver will react with chloride, AgCl. All halides are soluble except for silver, mercury, lead. So we have two things that are going on in this reaction, in this problem. We have silver reacting with the chromate to form silver chromate, insoluble salt. We have the silver reacting with the chloride to make silver chloride, insoluble salt. All right, and 0.015 molar. All right, so the question is, what is our concentration of Cl minus? All right, so this is where our Cl minus is. We want to know what that is at equilibrium. We're starting initially, we have 0.015 molar. We want to know where does that end up. And that is when this just begins to precipitate. So when you have your KSP equal to your QSP, that's when it's going to just start to precipitate. So that means it is just starting to precipitate. All right, so it's at equilibrium. You add one more drop of your Ag plus, you're going to get a precipitate. So when it's exactly the right concentration, then you're going to add one small drop of Ag plus, then you're going to get a precipitate. All right, so we need to know what our concentration of Ag plus is when the KSP is equal to our QSP. So it is the exact same setup. And so your KSP, we have to look that number up. Your KSP is 1.1 times 10 to the minus 12. And then the KSP, we will also need it for the silver chloride. And, well, maybe we, 1.8 times 10 to the minus 10. 1.8 times 10 to the minus 10. All right, so what we need to know is what is the concentration of Ag plus when this starts to precipitate. So when you have your 1.1 times 10 to the minus 12 equals to your Ag plus concentration squared times your CrO4 minus 2, which we know that concentration, that is 0.015 molar. All right, and this number that we get for Ag plus, all right, so we divide both sides by 0.015. We divide both sides by 0.015, and then we have to take the square root. And when you do that, you get an Ag plus concentration of 8.6 times 10 to the minus 6. So if you added 8.6 times 10 to the minus 6 here, that's when your KSP is equal to your QSP. One more drop and microliter drop, and you're going to get a precipitate. That's just when it starts to precipitate. So that is our concentration of Ag plus. And so then we put it here. 8.6 times 10 to the minus 6, that is our concentration of Ag plus when our silver chromate starts to precipitate. So now we can calculate the QSP here. So that is your Ag plus concentration times your Cl minus concentration, because the question was, do you get a precipitate? No, it doesn't. The question is not, does it precipitate? The question is, what is the concentration of Cl minus? All right, so now it is not a precipitate question. So that is equal to 1.8 times 10 to the minus 10. All right, so we now know our silver plus 1 concentration. It is 8.6 times 10 to the minus 6. What we want to know is not the concentration of Cl minus initial. We know that it is 0.015. What we want to know is what is our concentration of Cl minus at equilibrium. And this is how we find it, because we're putting it in as KSP, which is our equilibrium concentrations, 1.8 times 10 to the minus 10. And when you divide both sides by your 8.6 times 10 to the minus 6, you get your Cl minus concentration. And your Cl minus concentration is 2.1 times 10 to the minus 5. Which also answers the question that I keep asking, does this precipitate your silver chloride? And the answer is yes, AgCl will precipitate. And we can solve that. We know that because it is not, if the answer was no precipitate, then our concentration of Cl minus would be the same, 0.015 molar. All right, but we can answer this question as well. And anytime you answer this question, you should be comparing your Q to your K. All right, so you take your KSP and you compare your QSP. All right, so we know our concentration of Ag plus at the initial state, 8.6 times 10 to the minus 6, and our initial concentration of Cl minus. So when you take your 8.6 times 10 to the minus 6 times 0.015, you get a Q value of 1.3 times 10 to the minus 7. And our KSP is 1.8 times 10 to the minus 10. All right, and you see that your KSP is much less than your QSP. Reaction goes to the left, and you get a precipitate. So I knew that we would get a precipitate since our Cl minus concentration was less than the 0.015. How did that happen? The reaction went to the left, forming the Ag plus. So that is a difficult question. There's a lot of things going on at the same time in that problem. All right, 1760. Which salt would you expect to dissolve more readily in acidic solution? And that is SR, strontium SR3, PO4 sub 2, or strontium sulfate, SrSO4. So we write the KSP reactions. All right, so when we add acid, H plus, so we're going to react that with the negative ion, PO4 minus 3. All right, and so, and this one can do it, we'll just say we have strong acid here, and that's going to give us H3PO4. This is not a memorized strong acid. This is a weak acid. All right, and so this is, of course, a strong acid. And so this equilibrium is very, very, very strongly going to the right. Yes, right. This is the right side. All right, so the equilibrium is going to the right. This is going to be a very large K value. All right, so it's 1 over the Ka, in this case, 1 over the Ka, well, multiplied by the Ka1, Ka2, Ka3. Here you have your 2H plus reacting with your SO4 minus 2, and that's going to give you H2SO4, which is a strong acid. And this one, the reaction does not go to the right. It goes to the right maybe a tiny little bit, but barely goes to the right. All right, so this would be a very small K value. All right, and so that reaction basically doesn't occur. So this reaction is very fast, going to the right. So what is this doing? Well, it's taking our PO4 minus 3, and it is reacting it. And so this equilibrium is going to shift to produce more of this phosphate. So here what we're doing is removing PO4 minus 3 by reacting with H plus. All right, so Le Chatelier's principle, you remove a product, the equilibrium is going to shift to form more of that product. And so you're going to have a much higher increase in solubility for your strontium phosphate. All right, so when you get these problems, you're always going to have an anion that's going to give you a weak acid and an anion that's giving you a strong acid. The anion that gives you the strong acid, that affects your solubility very, very minor, if at all. The one that forms a weak acid greatly increases your solubility. All right, 1764. All right, the formation constant for complex ion zinc hydroxide is 2.8 times 10 to the 15th. All right, so that is our zinc plus 2 reacting with 4 OH minus to give us our ZnOH sub 4 minus 2. So we are forming that. All KFs are very large. That means the reaction goes to the right until something on the left is 0. Then you can reach equilibrium. All right, so what is the concentration of the zinc plus 2 ion in the solution that is initially 0.2 molar zinc OH4 minus 2? All right, so initial. And of course, if you would prefer to do this problem in the reverse direction, you can. Remember that your KF, if you reverse it, that's called a KD. So your KF is the forward reaction. Your KD is the reverse reaction. So your KF, it's equal to 1 over KD. All right. So this is the given answer for the forward reaction of forming a complex ion. If you want to find the dissociation of the complex ion, that is called KD. You get that by taking 1 over your KF. All right, so you can reverse this reaction and take 1 over the KF to get the KD. You will get the exact same answer. I'm going to leave it as written. The KFs are large. I'm going to write it as a KF, and I'm going to do the problem as a KF. All right, so you can't have zeros at equilibrium. So this is minus x, and this is a very small number. So you're going to neglect that. So you got your plus 4x, and you got your plus x. So at equilibrium, we have x, we have 4x, and we have 0.20 molar minus x that we are going to neglect. And now we are just going to solve for x. But before we do that, we got to write the KF expression. This is an ion. All ions are aqueous. So it is a ZnOH sub 4 minus 2 concentration over the zinc plus 2 concentration and our OH minus raised to its coefficient of 4. All right, and so now we just plug in our equilibrium numbers. We have 0.20 molar. We have x. We have 4x raised to the 4th. And we been given the number for that KF. It is 2.8 times 10 to the 15th. All right, so when you have a large number, that means that you're going to have a lot of products, very few reactants. So when this started with 0.2 molar of our product, very little is going to go back to forming some reactants. It is going to be some amount. You cannot have zeros at equilibrium. All right, so now you've got to solve for x. All right, so when we rearrange this, we have to multiply both sides by x times 4x to the 4th. So we're going to multiply both sides by x and 4x to the 4th. Now we're going to divide both sides by 2.8 times 10 to the 15th. Divide both sides by 2.8 times 10 to the 15th. All right, we also have to get rid of 4 to the 4th, and I don't want to calculate 16 times 16, so I'm just going to leave it as 4 to the 4th. And so I'm going to have now divide both sides by 4 to the 4th. 0.20, now I've already divided by 2.8 times 10 to the 15. And now I also have to divide by 4 to the fourth. And that, when I divide this by 4 to the fourth, because when you multiply that out, that's 4 to the fourth, x to the fourth. So I'm getting rid of my 4 to the fourth. And so then I have x to the fifth. Then I take my fifth root of both sides to get my x value. And when I take the fifth root of that, I get 1.9 times 10 to the minus 4. All right, so, and that is my answer. So this is x. And so when I look up here, that x value is the zinc plus 2. So the question was, what is your concentration of zinc plus 2 at equilibrium? And that is your x value. It is a small number. It is a 1.9 times 10 to the minus 4 molar. So your zinc plus 2 concentration is equal to x is equal to 1.9 times 10 to the minus 4 molar. Now, if we wanted the OH minus concentration, that is equal to 4x. And if you multiply that by 4, you get 7.8 times 10 to the minus 4. And then you can find your POH. You take the negative log of that, you get your POH. And the negative log of that is a 3.11. And of course, no one asked for the POH. They all asked for the pH. And so that is a 10.89. All right, so in this problem, they didn't ask for the pH, but that is a question that I would ask. What is the zinc plus 2 concentration? What's the OH minus concentration? What is the pH? All right, so you would then get the POH and then get the pH from that. Again, if you do that in reverse, you get exactly the same answer. You get the exact same x value, 1.9 times 10 to the minus 4. You would get the same OH concentration and the same pH. So if you prefer to work with small k values, you can reverse it, and you will have your small k value. All right, that was 64, 66. All right, predict whether nickel hydroxide will precipitate. All right, so anytime I hear that, I think I have to calculate a Q. Will it precipitate from a solution? That is a bunch of stuff. All right, so we got 0.0020 molar of nickel sulfate. We've got 0.010 molar of sodium hydroxide. And we've got 0.1 molar of NH3. All right, and so we have two things going on here. We have nickel hydroxide, which was the question. Will nickel hydroxide precipitate? So that's a solid. And so you get Ni plus 2 and 2OH minus. And you go to the chart, you find your KSP for nickel hydroxide. It is 2.0 times 10 to the minus 15. We are also given a KF, and that is for our Ni plus 2 plus 6 NH3s in equilibrium with our Ni NH3 sub 6, and that's plus 2, and that has a KF off the chart. 5.6 times 10 to the 8th. All right. So the question is, will nickel hydroxide precipitate? So what that tells you is that you're going to have an initial nickel plus 2 concentration and a nickel hydroxide concentration. All right. So we could answer that. All right. So these are completely soluble. Well, that's just NH3. But this salt is completely soluble. This salt is completely soluble. So you get Ni plus 2, you get SO4 minus 2, you get Na plus, you get OH minus. So 0.0020 completely going to the right. All right, and so we have 0.0020 molar, and here we have 0.10 molar. Here we have our 0.0020 molar, and here we have our 0.010 molar. All right, so you could have two questions here. The question would be, will it precipitate before we added the NH3? All right, so before NH3, you would find your Q, that is your nickel plus 2 concentration, and your OH minus concentration squared. So if you take your 0.01 and you square it and multiply by 0.002, you have a 2 times 10 to the minus 7. And so you compare your KSP versus your QSP. You have a 2 times 10 to the minus 15. You have a 2 times 10 to the minus 7. All right, and so you definitely would get a precipitate. All right, but now the question is, we're not just in water, we are in 0.1 molar NH3. So what's going to happen here? Well, what happens here is this reaction is going to go to the right until something on the left is 0. You have a very large Kf value. So minus x, minus 6x, and plus x. And so this is going to 0. So your x value is 0.002. And so you have 0.0020 here. So minus that, you get a 0.088 molar. And you get a 0.0020 molar. All right, of course, you cannot have a 0 at equilibrium. Our nickel plus 2 is going to be small, but you're going to have the small amount going back, your small amount going back, you neglect that, 0.088, 0.0020. All right, so you calculate your x value. So your Kf is your Ni NH3 sub 6 plus 2 Ni plus 2 NH3 raised to the 6th. So you plug in your numbers, 5.6 times 10 to the 8th, your 0.0020, your x, your 0.088 raised to the 6th, and you get your x value of 7.7 times 10 to the minus 6. So that is your nickel plus 2. So now when you find your Q by taking your nickel and your OH minus squared, you get a Q value now, since we added the NH3, of 7.7 times 10 to the minus 10. But that is still too big, and you still get a precipitate. All right. That is all for today. I will put